Welcome to This Explainer. Today, we're diving straight into the hidden mathematical choreography that's literally governing everything around us. From the exact way an apple falls from a tree to how a multi-billion-dollar spacecraft navigates the absolute vacuum of space, the rules of three-dimensional motion are quietly dictating our reality. And the truth is, the physics of how things move in our 3D world is infinitely more fascinating, complex, and honestly sometimes downright bizarre than we give it credit for. By the end of this, we're going to completely change how you see the very space you're sitting in right now. I mean, think about it for a second. Why doesn't a spinning top just fall over? We deal with three-dimensional motion every single day, yet it constantly defies our basic, everyday intuition about gravity and movement. Gravity is pulling straight down on that top, right? Yet instead of falling, it seemingly defies nature and just dances upright, perfectly balancing on a tiny little point. Phenomena like this happen because moving in 3 dimensions unleashes a wildly complex set of mathematical rules that just don't exist when you're only moving in a straight line. Here's the deal. When you add that 3rd dimension, depth, you completely change the rules of physics. In just 1 dimension, motion is super simple. You go forward or you go backward. In 2 dimensions, you can turn left or right. But 3D motion, it's infinitely richer, weirder, and full of these hidden loopholes. Suddenly, objects can rotate in multiple directions at once. Forces can pull on an object without actually doing any work on it, and rotations can violently destabilize without any warning at all. Things get beautifully complicated, and to understand it, we're going to need a special set of tools.
So let's jump straight into part 1, the language of space.
Okay, before we can decode all this physical complexity, we really need to understand the basic vocabulary that physicists and engineers use to map it out. We need a way to describe not just how fast something is going, but exactly where it's heading and the vastness of 3D space. Enter the vector. A vector is a mathematical object that has both a magnitude, or size, and a direction. Without vectors, it's literally impossible to map how things actually move in the real world. If I tell you a car is driving 60 miles an hour, well, that's just a scalar. It only has magnitude. But if I tell you a car is driving 60 miles an hour straight north, boom, that is a vector. And in 3 dimensions, vectors are the absolute lifeblood of physics. Velocity, acceleration, force, momentum, they are all vectors. So compare simple 1D motion to full-on 3D motion. A car driving straight on a flat, narrow road, that's a piece of cake to predict. You just need a speed and a positive or negative direction. But look at 3D motion. It requires vectors, complex mathematical operations called cross products, and entire coordinate frames just to track a single object. When you multiply vectors in 3D using a cross product, the order actually matters, and the result is a brand new vector pointing in a completely new perpendicular direction. That is exactly why predicting the path of a tumbling asteroid is so much harder than predicting a car on a straight track. Which brings us to part 2, jerk, snap, crackle, and pop. So what happens when your acceleration itself changes? Well, you start moving up this crazy hierarchy of motion derivatives. We're really escalating the complexity here by looking at the hidden layers of motion that you feel in your bones every day, but probably never talk about. Step 1 is your position. Change your position, you get step 2, velocity. Change your velocity, you get step 3, acceleration. But change your acceleration abruptly. That is step 4, jerk. You feel jerk when someone suddenly slams on the car brakes. It's that harsh physical jolt. Roller coaster engineers actually obsess over minimizing jerk to keep you from getting whiplash. But we don't stop there. Change the jerk, and you get step 5, snap. Snap is heavily used today for predictive motion, like calculating the incredibly smooth trajectories needed to fly autonomous quadrotor drones. And yes, it keeps going. If you keep taking the derivative of motion, you get to steps 5 and 6, which brings us to this amazing quote from our sources. The 4th derivative is referred to as snap, leading the 5th and 6th derivatives to be sometimes somewhat facetiously called crackle and pop. That's right. Elite theoretical physicists and engineers officially named the extreme, highest-order kinematic derivatives of the universe after the Rice Krispie cereal mascots. I mean, you can't make this stuff up. While crackle and pop are rarely used outside of predicting highly complex human motion, it's a fantastic reminder that physicists definitely have a sense of humor. All right, let's pivot to part 3, the weirdness of rotation. If you thought moving in straight lines in 3D was complex, spinning in 3 dimensions is just totally mind-bending and deeply counterintuitive, because things in our world rarely just move forward, right? They tumble, they spin, they orbit. First off, let's remember we live on a rotating sphere. Because the Earth is spinning, it creates a non-inertial reference frame, which gives rise to something called the Coriolis force. Now, this isn't a physical push. It's a fictitious force caused purely by the geometry of 3D rotation. but its impacts, they are absolutely massive. The Coriolis force dictates the counterclockwise rotation of atmospheric cyclones in the northern hemisphere. It shapes the major ocean currents across the entire globe. It's even responsible for the eastward deflection of long-range ballistics, meaning if you fire an artillery shell hundreds of miles north, the Earth actually rotates out from under it, making the shell curve to the east. But hey, quick myth bust here. As much as we love the Coriolis force, it does not cause your bathtub drain to spin in opposite directions in different hemispheres. The Coriolis effect is way, way too weak at the tiny scale of a household bathtub or a toilet to dictate the water's spin. At that scale, the spin is determined entirely by the geometry of the drain itself and the residual angular momentum of how the water was poured in. You literally need the massive scale of kilometers and hours for the Coriolis force to actually take control. So the really crucial point here is that 3D rotation hides these wild instabilities, which brings us to the tennis racket theorem, also known as the Johnny-Bekov effect. If you take a rigid body with 3 different axes, think of a tennis racket or a thick book, and spin it, something incredibly strange happens. Rotation on its largest axis is stable, rotation on its smallest axis is stable, but rotation on the intermediate or middle axis, it's violently unstable. If you toss a tennis racket into the air spinning on that middle axis, it will spontaneously and chaotically flip over mid-flight. This is all due to complex, nonlinear cross-coupling in 3D mechanics. Cosmonauts have even observed this exact spooky flipping effect up in microgravity in space.
And this mathematical weirdness, it has massive real-world stakes. To track 3D rotation, engineers historically used 3 intersecting rotation angles called Euler angles. During the Apollo 11 moon landing, the lunar module actually faced a terrifying phenomenon called gimbal lock. This happens when 2 of those rotational axes accidentally align with each other. When they align, you instantly lose an entire spatial degree of freedom. Your math simply breaks down, and you literally lose the ability to track which way your spacecraft is pointing. This highly theoretical math had actual life-or-death consequences for the very first moon landing.
Moving right along to part 4, relativity and quantum motion. So we've talked about baseballs, drones, and spacecraft, right? But what happens when we zoom way out to the size of entire galaxies, or zoom way in to the size of atoms? Do these same rules apply? The answer is yes, but they distort in some totally fascinating ways at the extreme limits of our universe. For over 2 centuries, classical Newtonian physics told us that we live in a 3D space with an absolute, ticking clock of time running in the background. But Albert Einstein completely shattered Newton's framework. He proved that when you move at speeds nearing the speed of light, space and time are not separate things. They actually merge into a single, interwoven 4D fabric called spacetime. In this framework, to calculate motion, you don't just have a 3D velocity, you have a 4 velocity. And things like the mass of an object effectively increase as you push the speed limit of the universe. And there's this stark, wild contrast between the macro and the micro. On the macro scale, planets and stars, motion is governed by general relativity. Gravity isn't just a pulling force anymore, it's the actual curving of 4D space-time. A rotating planet literally drags the fabric of space around with it, an effect called frame dragging. But jump down to the micro scale and things get incredibly weird again. Subatomic particles don't have exact predictable trajectories, their motion is governed by probabilistic wave functions. They also have an intrinsic property called quantum spin. They have angular momentum, but the electron isn't actually physically turning like a top. It's a purely quantum mechanical 3D vector property. It's just wild. And finally, part 5, the frontiers of motion. Mastering these mathematical extremes, from snap all the way down to quantum spin, is exactly what's driving incredible modern technologies today. Between 2024 and 2026 alone, we've seen massive breakthroughs. Researchers have developed cutting-edge AI systems like OmniPhysics-Gs, which use highly complex physics to perfectly render and simulate how different materials, like fluids and elastic solids, interact in 3D space. Drone engineers are using advanced minimum snap trajectory calculations to make autonomous quadrotors fly smoother and faster than ever before. And physicists are actually manipulating that intrinsic 3D quantum spin of electrons to build the foundational architecture of next-generation quantum computers. Which really leaves us with one final, profound question to ponder today. Is the very fabric of our everyday movement just a localized illusion of a much grander 4-dimensional space-time geometry? Think about it. When you reach for a cup of coffee, are you just following a localized geodish in a curved universe, constrained by invisible vectors, Coriolis effects, and quantum probabilities? The hidden choreography of the universe is happening all around you every single second of the day. Thank you so much for diving into the hidden geometry of 3D motion with me on this explainer. Keep observing, keep questioning, and I'll catch you on the next one.